Okay, so this is 14.3, integration by parts. So for this integration by parts, I'm just going to talk a little bit about what it is. So initially you have an integral of u dv, which is just some function u and some differential dv. If you have those, then you can say that it's equal to u, the function, times v, the function, minus the integral of v, the function, and du, the differential. So you see that there's some change from differential to function, from function to differential. This is sort of an interesting quirk that happens in integration by parts. So it comes from the product rule. If you wanted to look at the product rule and integrate both sides, you would get basically the integration by parts formula. So you do the derivative of u of x times v of x. That's equal to u prime of v, or u prime of x times vx, plus u of x v prime of x. And then if you integrate both sides, you'll get the integral of that d over dx of ux vx with respect to dx, which would be equal to the integral of that product rule that we talked about with respect to dx. And if you use the substitutions that du is equal to u prime of x dx and dv is equal to v prime of x dx, then you would get u times v equals the integral of v du plus the integral of u dv. And so that, if you rearrange it slightly, would give you the exact formula that we have for integration by parts. So that's a little bit of how the derivation goes. If you're going to use this, usually you would choose some u and dv in order to substitute in for this particular formula and come up with a nice little integral of v du, which would be easier for you to solve than what you had originally. So in summary, for the integration by parts formula, the integral of u dv equal to u times v minus the integral of v du. You would have some u dv, which is the original integral, and you would pick an integrable dv, so be able to create your v from that differential dv. And you would take your integral of v du, and it would be simpler than your integral of u dv. You usually don't want to try and make yourself work harder by doing integration by parts. You want to be able to work more efficiently, easier by doing integration by parts. So try to pick a integral of v du, or pick your v and u, dv and u, in such a way that your integral of v du is easier than your integral of u dv. Particular examples which can be used in order to simplify things are if you have f of x equal to x to the p e to the ax, then you can take u and set it equal to x to the p, and dv equal to e to the ax times dx. This allows for you to be able to integrate this and reduce the exponent of that x to the p for the next step by 1. This means that you can do another integral or integration by parts if you haven't reached 0 for that exponent. And that allows for you to continue this process until you do reach 0. So you just keep integrating by parts with this x to the p, reducing it by 1 each time until you reach 0. And then you'll have all these terms that you'll eventually add up. But what you have is a process that gets you to where you need to be in order to solve it. Same process can happen with your f of x if x to the p times the quantity ln of x to the qth power is what your function is. You can try u equals the quantity of ln of x to the qth power, and set your dv equal to x to the p dx, which is the remainder there. And so this would be the solution, or this would be the process that you'd go through for this form. And again, you'd end up with some stuff that you would need to kind of work out. But this is an interesting kind of result in and of itself to just sort of look at and work with. So, all right, that's the end for 14.3. I'll talk to you guys later.